Is COG scalable? We're going to go set out to answer this question. The conclusion is answering this question, but we have to get through a bunch of slides first to formulate our opinion on whether or not this data format is actually scalable. My name's Jeff. I'm a principal software engineer at Regrow. That's my day job. Regrow does experience some of the pain points I'm going to discuss in this slideshow. This talk has nothing to do with Regrow. Over the last 5 years, I've spent a lot of time just working with the COG data format. I've sort of learned how to code through the lens of COG. So this is kind of a project that's been with me ever since I started coding about 7-8 years back. First thing we need is a COG. This is a beautiful COG. It's from the Landsat Analysis Ready Data Collection. It's somewhere in the Midwest. I don't remember exactly where, but there's lots of field boundaries. The other thing we need something to serve this COG in order to see if it's scalable. We're going to use a tile server as an example just because I thought that it would be I thought that most people here would understand or have worked at a high level with a tile server. Also, mathematically, they're very straightforward, so they're quite easy to simulate. This is what a tile server looks like when you deploy it. If you've ever deployed T-Tiler, this is kind of what you end up with, or if you're deploying it through EO API. You have a caller, usually this is a web map, or maybe it's something else that's trying to fetch imagery. It's going through some sort of ingress, and you have your tile server deployed multiple times across multiple replicas. And these are, of course, just serving data out of S3. Now, blob stores is the main character in this story. The great part about blob stores, and the reason I like them over databases, is they're so incredibly simple to work with. There's only a couple things you need to know. The first is that the number one thing when it comes to performance is time to first byte, which is essentially the amount of overhead that is incurred when you open a new connection to the blob store. Once that connection is open, data transfer through that connection is extremely cheap. It doesn't really matter how much data you pull down. It's generally going to be quite performant. The other thing to understand is that S3, which is what we're using as an example here, supports at least 5,500 GET requests per second per key prefix. Experimentally, it's not 5,500. It's closer to 8,500 to 15,000 is what I've seen from benchmarks. And if you're not familiar with what a key prefix is, it's just that green part of the key. So the red part is the bucket name, the green part is the key prefix, and the blue part is the object name. So basically everything under this one directory shares a rate limit of 5,500 gets. This means that scaling blob stores is actually super easy. You just have to do two things, right? You have to send as few requests as possible to get the data you need, and you need to send those requests as fast as possible. If you can do these two things, then generally access to COG or ZAR or GeoParquet or really any data format that's hitting the blob store is going to be fast. So now we're going to talk about a couple kind of things happening behind the tile server. The first thing is we need to serve some COGs. And while COG is an optimized format for the cloud, not all COGs are optimized for the cloud. So the internal structure greatly matters, as we just saw with the Landsat case study. Because this is a tiling use case, I decided to go with a web-optimized COG. Oh, is that upstairs? Oh, that's cool. Thanks, guys. This particular image is aligned to this specific XYZ tile. It's 8,192 pixels by 8,192 pixels, and it covers the entire cross-section of the quad tree up until zoom 12. Keep this in mind. We're going to be using this image for the rest of the presentation, so just kind of keep the dimensions in mind. This is showing how you can kind of zoom in through the overviews. This is just basically going from zoom 7 at the very top down to zoom 12 at the very bottom. This, again, is a web-optimized COG. It's at zoom 7. There's 16,384 zoom 7 tiles in the world. So if you wanted to create a global tile map, you'd have, or a global web map with this data, you'd have that many images. And the important thing to call about web-optimized COGs is that it takes a single request to fetch the header, generally, to fetch the first 32 kilobytes of the COG. And then it takes a single fetch to request the block, because the blocks are aligned with our XYZ tiles. So in theory, this is the most optimized COG layout that we can use for this tile server use case that we're building. There's the GDAL info on the right for provenance if you want to go back and look at it. We can also use this cool library called TileBench, which GDAL logs out a bunch of information about what requests it's sending, and this parses those logs into a structured form and tells you what it's doing. And so we can use this to confirm that I can request this specific tile 10.225.395, and it does actually only send 2 requests. The next big thing is caching. If our goal is to reduce the number of requests, I'm gonna get my phone out to make sure I'm on time. If the goal is to reduce the number of requests, then caching is obviously one of the first things that comes to mind, is if we've already requested something, we should cache it and not have to request it again. Now, most applications have some sort of local cache, which is symbolized by these green boxes. Most people, I would say, who are interacting with the COGs are using GDAL or Rasterio. And GDAL actually has 2 caches. There's the VSI cache, which caches content coming through any of the VSI drivers. So this is going to cache stuff like COG headers and other sidecar metadata files. And then there is the block cache, which caches the actual tiles in the image. The important thing to understand is these are local caches. The cache in replica 1 cannot communicate with the cache in replica 2, which cannot communicate in the cache with replica 3. One of the things to understand with the ingress is there's a ton of different ways of load balancing requests from an ingress across a bunch of target servers. One of the common ways is round robin load balancing, where you literally just start with the first, and then you go to the second, and then go to the third, and then back to the first. It should be pretty clear to see from this animation that in order, if we're fetching 1 COG header, it takes 3 requests for it to be fully cached across all replicas. And this presents a pretty big problem in terms of scalability. The issue is that if you have perfect caching, if you fetch a header and you only have to fetch it once, your number of requests should be the same as the number of images you have. With local caching, which is the worst case scenario, with 100 images and 100 replicas of your tile server, so you have a lot of data, you're trying to scale horizontally to process it, you end up sending a lot more requests than you would if you did have a cache. Now, this is not a perfect simulation. Round robin is much more non-deterministic, especially when you consider a tile server. You don't really know when someone's going to request a header, so this is kind of very simplistic. So I wrote a little simulation model that simulates how this system works. I basically wrote some code that predicts for 100 replicas and 100 images how many requests is it going to take for all of those headers to be cached cached across all of our replicas. You run this simulation like 10,000 times, you plot the distribution, and you get this nice normal distribution. What we can then do is run this not just across 100 replicas, but a bunch of other replica counts. And you can see that in general, as you scale horizontally to process more data, you end up requiring significantly more requests to fully cache the image across your tile server, which sort of makes sense intuitively. The bad part about this is, ooh, what is happening there? Ignore the right side. I don't know what that is. This is really the bad part of this, is you can take this graph and turn it into a metric 0 to 1 of how efficient your cache is at different scales. And this is not good. This is a really bad graph. Because basically your cache starts really, really efficient, right, when you have a small number of replicas. And as you increase it very quickly, increases to basically close to 0 efficiency. So while, as you scale horizontally, and this doesn't just apply to tile servers, this applies if you're scaling across GPUs. Anytime you're scaling horizontally with some sort of scheduler that's moving these requests around, generally local caches become extremely inefficient to the point that they might as well not exist. So if you've ever taken like some Rasterio code, run it on like a single image and it's pretty fast, and then you deploy that code and try to run it on lots of images and it feels like it's going slow or it feels like it's dragging, this is what's pulling you down, is this cache inefficiency. So how can we fix this? There are a couple distributed caching patterns that we can use. The first is what's called cache aside. So we basically just move the cache to the side. That's why it's called cache aside. This is the most common pattern. I'm sure many people who code have implemented this, where you have an API and you have a Redis database and you just kind of throw data over there and you check cache hits, cache misses. The problem with this is it's quite inefficient because we're building a tile server, and after all, we want to pull data from a bucket. We don't want to have to go back and forth between this cache. And in the worst case scenario, it actually takes 2 round trips to and from Redis if there's a cache miss on the initial request. And those round trips to Redis are times that you are not actually requesting data from S3. This is also kind of hard to scale because most of the time when you deploy these things, you're using some sort of vertically scaled cache that doesn't scale elastically horizontally. One more modern approach that's become popular over the couple recent years is peer-to-peer cache. And so you still have a local cache, but these caches can communicate with each other. So if a request comes into replica 2, it'll ask its buddies, hey, replica 1, do you have this data for me? Hey, replica 3, do you have it? And if it does, it'll move it over. The best implementation of this is called group cache. It's written in Go. It's written by Google, and they use it extensively in their internal infrastructure as far as I'm aware. And it doesn't just manage like the peer-to-peer, it also manages moving data around, manages hotspotting of keys, and a bunch of other really nice things to make this super performant. You can also implement a forward proxy. This is a good solution if, to be clear, peer-to-peer caches are extremely new and difficult to deploy and kind of hard to work with. This is a much more common setup where you have some sort of forward proxy in between your replica and your bucket that acts as a cache. The downside with this is getting a bit nuancy, but S3 uses these things called HMAC keys to authenticate against S3. And the way HMAC keys work is the host creates a header that the server validates came from the original host, but because your request is going through a different host, it invalidates your HMAC key. So this type of forward proxy is great, but it only really works on publicly available data. If you have data that's private, you can technically teach the proxy how to authenticate against that data. That can be a security nightmare depending on what you're deploying into. Shameless self-plug, I do have a proof of concept of a forward proxy for GDAL. I would not deploy this to prod just yet. It works, and it's kind of cool because you can stand up the proxy and then run like a GDAL info call, and it's kind of slow, and then run another one, and it's like really fast. And so it works, and I've deployed it to Kubernetes for some like of my own personal test projects, but yeah, don't deploy this to prod just yet. This is using group cache, but because group cache is written in Go, we have to deploy it as like a sidecar container. Because Rasterio is written in Python, of course. The other thing that we can do, time check, we're good, is MetaTiling. MetaTiling is really straightforward. COGs are row major, which means blocks in the COG in the same row are stored adjacent to each other on disk. One of the problems I've seen a lot in the Zara community is if you have a chunk size that's not good for your application, you need to physically rechunk your data into a new data set that has a larger or a smaller chunk size depending on what you're doing, especially for temporal chunks. If you're doing like daily reads versus monthly versus yearly, the chunking can really matter. The nice part about MetaTiling is that you can logically increase the chunk size without changing the physical chunk size. So for example, we have our 8,000 by 8,000 image. It has a 256 by 256 chunk size. There are 1,024 chunks. One way of thinking about this is you could logically say the chunk size is 4,096 by 4,096. There's nothing actually stopping you from doing this. This shows the number of requests you're sending as you increase the number of metatiles, right? So very quickly, as you essentially implement this virtual tiling, you can see a massive drop in the number of requests. And again, one of our main goals is to reduce the number of requests coming to and from the blob store. Sending requests quickly, this is the last point I want to talk on. This one's pretty straightforward. I mean, I'm just going to give you guys some advice. Use async await where possible. It's definitely the most efficient. Lower level languages like Rust and Go that have concurrency built in are better than Python, where async await was kind of bolted on late in Python 3. Maintain strong data locality. This is huge. Data locality is incredibly important. Try to deploy in the same data center as your data. And always request COG headers in one request, which requires knowing your header size ahead of time, which can be a bit daunting at first, but I promise you if you set this to 32 kilobytes, it'll work for 99.9% of COGs in the wild. Sure, you'll run into a COG that's 6 terabytes and has like a 30 megabyte header. You won't run into those very often though. So now that we've gone over in theory kind of how this scales, let's look at in practice how this actually works. So I built a benchmarking tool. This is kind of, in hindsight, this is kind of ridiculous that I decided to do this. I wasn't happy with how the other Python benchmarking tools work. The main issue is that most of these tools work by, you have a function call, and you do like start and time the call, like return the results, and then you scale it. The problem is when you're testing IO-bound code, you often end up spending more CPU cycles timing your code than actually running the benchmark. And so I built a brand new benchmarking tool that decouples, thanks guys, that decouples the running of the test from the generation of metrics. And that lets us basically run really clean tests that are repeatable, even though it's IO-bound, which is pretty cool. I've had a great time developing this tool because you can run the same test like 3 times and you get like the exact same number, which is just crazy for IO-bound code because usually that's just not how it works. It also supports a bunch of different libraries, so a lot of the work here was me looking into all these libraries and how they're configured and trying to configure them so they're all the same to reduce the number of independent variables that are changing across tests. Some of these aren't as well supported. HTTPX, I'm not sure what's going on there. FSSpec works on my local but breaks on the instance. The other ones are pretty fine though. So as I was saying, one of the things this does is it decouples the generation of the metrics from the running of the tests. The way this works is by digging into the Prometheus and Grafana stack, which I basically deploy a bunch of containers. And then I have Prometheus and Grafana over here as other containers in CAdvisor, which is Google's container monitoring tool. And those things monitor my test containers and give me information about stuff like network, memory, CPU, and other information like that. Prometheus has a query language called PromQL. It's really hard to see with the lighting, but what that is doing is it's basically saying, find me, I almost spilled my water all over my computer. That would have been bad. It's basically saying, find me all of the network bytes that these containers used, sum them across this run ID, which is this like join key. Each one of these curves is actually the sum of 20 containers running. So we're taking all of our individual containers, summing them together. And what's happening here is I'm increasing the chunk size. So I believe this first test, the chunk size was 16 kilobytes. I believe the last test, the chunk size was 8 megabytes. This is really nice because if you want to, for example, calculate the total number of bytes that was sent in one of these tests, you can just calculate the area under the curve and you're good to go. Header requests, this is where we end up with header requests. Rasterio is super slow. AIOHTTP and AsyncTIF are much, much faster, both in terms of requests per second and megabytes per second. But all these libraries are parsing the COG header, by the way. So this is sending an HTTP request and then parsing the header into some type of structure. MetaTiling, Rasterio really, really struggles without MetaTiling. When you implement MetaTiling, it does a much better job. But even Rasterio MetaTiling is slower than AsyncTIF with regular tiling and AIOHTTP with regular tiling. All the methods benefit from MetaTiling, which is pretty cool. Especially AsyncTIF gets a lot faster. I think it goes from like 1.5 seconds to dump all 1,024 tiles to about half a second, which is just crazy fast. This is what we were looking at here, but in CSV form, and then into a matplotlib diagram. And so you can see that as we increase chunk size, our throughput goes up. And all libraries respond quite well to chunk size, except for HTTPX, which had a bug in this test. So ignore that one. So we have about a minute left, which is perfect timing. Back to our question, is COG scalable? I think the answer is yes. Yes, it is. But I don't think our software is written in a way that encourages or achieves scalable system design in the cloud. And that really holds back the potential for scalability that you see, and not just COG, but other data formats as well. Software, hardware, and data are in constant coevolution. Code doesn't age, but context does change. And context has changed very quickly. That's why we're all here. As the CNG community standardizes on individual data formats like ZAR and COG, it makes a ton of sense to invest more in specialized tooling for those formats. The reality is if you're looking to not use Rasterio or Rio X-Ray, there's not really many options in the COG space, although I'm very excited for the workshop tomorrow to see how we can virtualize COGs into ice chunk space. That would be pretty cool. Now, lastly, I just want to, Kyle, I'm going to take into your time and talk about your own libraries. Like if you don't believe the theory and the numbers and stuff you saw here, there are several places where people are challenging the status quo on how these works, on how our tooling works. Lawnboard is a great example that's really leaning into GeoAero and GeoParquet to massively speed up the amount and increase the amount of data we can visualize in Jupyter notebooks. This absolutely blows Folium out of the water, but Folium was written before GeoAero and GeoParquet existed, right? So again, code doesn't get old, but context does change. This X-Array community recently rewrote Zara Python v3 because the v3 spec's very different than v2 and saw big performance increases. This reported 14x performance increase. And of course, IceJunk has shown big performance increases as well, rewriting a lot of the I/O from Python into Rust. That's it. Any questions? We're kind of running into Kyle's time, so maybe one question, and then we'll jump over to Kyle if anyone has questions. And feel free to find me after, ask questions.